Hello class, welcome to the third segment in chapter 4 where we're covering ratio and regression estimation. So far we've looked at the motivation for why you might care about estimating a ratio. We've also examined when ratio estimators might be better suited for estimation, even though ratio estimators are generally more biased than sample mean estimators or sample total estimators that we have seen or learned about in chapters 2 and 3. We've seen that under certain conditions that the ratio estimators themselves can be far less variable and have smaller variance. So the overall mean squared error for ratio estimators can be smaller than that for sample mean estimators or sample total estimators, even though those estimators are generally unbiased under many designs. So we've specifically identified those scenarios where coefficient of variation between the x and the y variables are similar, where the x variable has a small population mean, and so on. So we've gone through those conditions in the last segment, so revisit those if you are wondering about that. We also said that generally positively correlated variables with the outcome that we care about are generally preferred, and usually that would be described as a regression line through the origin, for example, where we care about positively correlated covariates that we know for every element in the population. So we've already gone through the formulas, we've already gone through a little bit of the derivations of those variance estimates, and now we're going to talk about how to do this in R, and I'm going to go through a couple of examples, and I'm going to encourage you to try these on your own as well. So in R, the survey package that we've been using all the while has a couple of functions here for survey ratio. So the survey ratio function So if you use the survey ratio function, you're going to specify the numerator variable, which is this tilde y var. That's the first variable it's expecting. That's the numerator variable. You're going to specify the x variable. That's the denominator variable. That's the tilde. And don't forget, the x var lettering here refers to the actual variable that is the x variable in your data set. But you have to start it with this prefix of this tilde. And that's really an idiosyncrasy of the survey package in R, just to make sure that it knows that you're grabbing a variable inside of the data set. So don't forget that notation, or you might not get this to work. You'll also specify your design, which we've talked about in chapters 2 and 3. For these examples, we're really going to use a simple random sample without replacement, but generally speaking, you can do these ratio estimates for stratified designs, for cluster designs, etc. So you'll need to make sure that you have a design object specified before you run the survey ratio function. Now the survey ratio function, as I mentioned, is going to get you an estimate of b hat and its standard error. If you want an estimate of y bar ratio, then you're going to need to use the predict function with the ratio object already run, and you're going to specify an x bar u number, and then if you want the standard error, you can choose standard error equals true. So this ratio is required because remember that y hat ratio is equal to the b estimate multiplied by x bar u. So essentially, this is why you have the predict function, because it's actually giving you a prediction score based on knowing the b, which is describing the regression relationship between the two variables, and the number that you want to use for creating the projection. We know that x bar u in a regression scenario is going to project us back up to y bar u. So this is going to be the closest estimate that we have to y bar u. If you want the total an estimate of the total and not the overall average in the population, you're going to use the same predict function. You're going to use the same ratio object, but in this case, you're going to actually specify the total for the X variable so that you get the projection correct. So instead of projecting to the sample mean or the population mean scale, you're going to project to the population total scale. So you need to have the total here, because remember, the total for a ratio estimator is our B hat multiplied by the total X in the population. So again, this is a projection type estimator, or a predicted value, if you will. And that's exactly why we're using the terminology predict here. And then of course, SE equals true. This is actually asking for the standard errors to be computed for you according to the formulas that we've talked about already, or their operationalization in a complex sample design where you're actually incorporating the sampling weights into those formula as well. Okay, so that's the setup for the R, how to do ratio estimation in the R package. Given what we've already learned about specifying the design, we have a couple of new, we have a new function that's going to serve as the basis here. That's going to get us our estimate of B, and then we're going to use that estimate of B, and along with the particular population values of the parameters that we're going to use to calibrate or predict our get our predictions or get our estimates. Okay, so we're going to look at how to do this in R. This is our previous example that we've already worked. I'm going to show you how I redo this in R. I generated the sample with a seed of 400. This just allows me to draw a sample of size 13 without replacement from the nursing data. We've already done this several times in the previous chapters. This shouldn't be new. In order to specify the survey object, we need to specify the FPC. And in this case, this is just the population total. And we're going to append that to our new nurse sample data. And then I'm going to create a survey design object. I'm going to give everybody the same an ID of 1, because everybody has just each case is its own ID. And then the strata is null. We don't have any stratification there. The data is the new nurse SAMP data, which includes this FPC variable that I just computed. Now I'm going to calculate the mean estimate for the patient expenditures using the survey mean functionality. So this is just specifying the patient care revenue data that I've collected, or that variable, the design that we've specified, and then I want design effect is true. You can take it or leave it for the design effect. And then I'm going to specify the ratio estimate, but the ratio estimate is in 2 steps. First, I need to get the B, so this is going to give me the B. And again, I need to specify a Y variable here. That's the numerator variable, and the X variable. So don't forget, your Y variable comes first, then your X variable. So this is the numerator, this is the denominator, this is the auxiliary variable that I'm using for the ratio estimate. And then this is the design object, and of course I want the standard error. And then I will print out this ratio estimate just to make sure that we got the same idea. And then I'm going to use the predict function, and in this case I'm using the ratio estimate object. This is X bar U, this is the average total patient days per facility in the population. And then the standard error is equal to true. So this function here is going to give me an estimate of the average patient care revenues per facility in the population. We already know what those answers are, at least when we did it by hand in the Excel calculators. Let's check our work here. It looks, so when you get the ratio estimator here, and stratum is just 1 because we don't have any strata, so it just gives everybody the same stratum value. You get this output that says ratios equal. The way you read this is the Y variable, this is the X variable, and this is the B hat estimate. This is the standard error of the B hat estimate, and you will see here that you will get the patient care revenues and the total patient days accordingly. So if we were to predict this value, so this is the standard error of the B hat, not the standard error of the overall mean estimate from the ratio. So that is going to be in the next code here. So I'm going to predict what the ratio estimate object, my total again is x bar u because I'm trying to project onto the y bar u scale. And then the standard error is true. So my estimated y bar u is 13,088.5, and the standard error is 656.5. I believe that we saw these two numbers earlier in our example, in our calculations. So it's good to see that they match. And now we know how to do this in R. Let's look at another example just to make sure you're getting this. This is example, we're going to use the same nurse sample that we used in the prior. This should be in example 4.3. We're going to estimate the total amount of money spent on nursing salaries across the region. So now we're looking to project a total rather than an average. So we need to estimate this using the sample total, including a standard error. So we're not going to use a ratio estimate. And then we're going to use a ratio estimator where we reuse an auxiliary variable is the patient care revenues. This is the total is in hundreds of thousands of dollars. And so the patient care revenues, the total for the entire population for the X variable is $738,927, hundreds of thousands of dollars. We want a point estimate and the standard error based on the ratio. Now we want to ask the question, why is this a good variable to use for ratio estimation? What is the mean squared error estimate for both of these estimates for both the sample total and the ratio estimator? And we know that the true total for the y variable in our population, the actual parameter we're trying to estimate, is 198,267. Now I put this here because it's theoretically something that we don't know and we're trying to estimate it, but we're actually going to use that to create an estimate of the bias just to be able to calculate the mean squared error accordingly. So this is the relationship between the nurse data, nursing salary expenditures, and the patient care revenues. And you see that the coefficient of variation for one of these variables is 0.49, the other is 0.43. These are not the same, but they're close. Correlation is about 0.58. This is not as strong as we'd like, in part because of this outlier over here. This is a facility that has a lot of revenues and very little expenses. Maybe they don't have a lot of nursing staff. Maybe this is a patient care facility where they don't need nursing staff, but maybe need like assistance or medical assistance of some other sort. So that throws off the correlation strength a little bit, but in general, this correlation is pretty strong for observational data. And so we're gonna leverage this variable and see what we get. So I'm going to create the estimate from the total using the survey total function, which we've used before. The design object we've already specified in the previous example. The variable is already included in that data set, so I'm easily able to get an estimated total and an estimated standard error. The mean squared error is simply the, and this just gives you the sum, the ty in the population, which is the value that I just pointed out here. I'm using that to create a variable so that I can compute the mean squared error easily. So the mean squared error is basically an estimate of the total revenue. The object that I got here, and the number 1 just refers to the fact that there are 2 elements in this vector called total revenue. First element is the estimate. Second element is the standard error. So this is just pulling off this number 202,292 minus the total, and we're going to square it, plus the standard error squared to get the variance. So this is the bias squared plus the variance. Now, theoretically, we know this total revenue is unbiased. So this is just an empirical estimation of the bias and the variance squared, just so that we can be comparable across the 2 estimates. But in general, what you're seeing here is that the mean squared error is a pretty large number. Let's see if we get something smaller with the ratio estimator, because generally the ratio estimator, this quantity is going to be larger, but on par, this quantity should be magnitudes lower, so that when I add these 2 together, increases here will be well offset by really large decreases in the variance. Let's check it out. So in order to do this, I need to calculate the survey ratio. I need to identify the Y variable, which is the nursing salary. I need to identify the patient care revenues, which is the X variable, my survey object, and the fact that I want standard errors. Again, we were used to seeing this. Now we're getting an output. And again, this is telling me that the Y variable is nursing salary, the X variable is patient care revenues, and my B hat estimate is a little over 0.3. The standard error for that B hat is a little over 0.01. Now, if I want to get the total for the ratio estimator, I'm going to use this predict function with my ratio estimate object that I just computed. I know that the total for the patient care revenues in the entire population, that's T sub capital X, is this 738,927. I know that I want to compute the standard error, so I'm going to ask R to do that. I'm going to print out this object. I'm going to get two components. One is the total estimate. The other is the standard error. Now, clearly, this standard error is a lot smaller than the previous. Let's go back to that slide for a second. The standard error here is 18,000. This standard error is 8,700. So it's actually about half of the variance. So this is, again, a magnitude of order difference. If I calculate the estimated bias and I square it and I add to that the square of the standard error, and I can pull this out by the object $ standard error because it's called standard error. It's telling me that right there. I'm going to get a number that looks like this, 739 and change. The previous page was 376, but if I look at the number of digits, 1, 2, 3, 4, 5, 6, 7, 8, 9, this one has 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is actually larger than what we would expect, in part because of the bias. Now here's the thing. We knew that the correlation between these two variables was not that strong, so we would expect that the bias would be small but not smaller. And so it is not surprising that we are getting a reduction in the variance, but the bias is still quite large given the magnitude of the variable we're estimating. Here this variable is in the hundreds of thousands, and so the magnitude is quite large. So even small misses on the bias could have devastating effects when we go to the mean squared error scale. So let's look at another example. I'm going to ask you to walk through this example on your own with an Excel spreadsheet, and then you can do it in R if you wish. Well, let me just explain the example and set it up to make sure we're all on the same page. I'll point you to the Excel spreadsheet. There is a solution in the Excel spreadsheet. There are two tabs in the example 45.xlsx file. On the first tab is the actual data that you see here. The second tab is the solution where all of it is worked out. But I would encourage you to try the solution first on the first tab before looking at the second tab, just to make sure you're understanding what's happening. This community, a couple of years ago, selected 10 inner city community centers from a network of 122 of them, randomly without replacement, in 2008. Participants from the community center participated in a Biggest Loser type weight loss contest, and they were deemed success if their final post-intervention weight was no more than 115% of their ideal weight. That means that they were almost close to their ideal weight or a little over. Patients were followed over 2 years and were re-interviewed or reclassified in 2010 using the same criterion. And that is, they were a success in 2010 if their 2010 weight was no more than 115% of their ideal weight that they specified for themselves in 2008. So the data are here listed. One thing you'll want to know is we want to estimate the proportion of participants who were still classified as successes after 2 years, along with the standard error and a 95% confidence interval. We'll use this t-distribution value here to create the confidence intervals. Now, why is this a setup for ratio estimation? You might be thinking the same thing. And clearly, it's possible that you could calculate the ratio of successes for each center. So the first center had 2 out of 6 were still classified as success. Second center, you can't compute that measure. Third center would be 3 out of 8. Fourth center would be 2 out of 2. fifth center would be 56 over 76. You can compute these ratios, and then you can take an average of the ratios and see what that estimate is. Certainly that's one way to do it, but the problem with that approach is that you've got some of these situations where you have zeros, and then essentially you're not able to compute that ratio. So that center doesn't contribute anything to the overall estimate of the proportion of participants who were still classified as successes. Now look, if a center had a lot of people in it in 2008 and none of them qualified for their weight loss goal, that zero is a real zero in our estimate of the number of people in that population who actually qualified for the weight loss. So we need not throw out the zeros. So if we compute the ratios at the center level, we will essentially throw them out and we won't be able to use them. But if we pull all this information together, we're getting an estimate of the denominator that looks at the total number of people in 2008 who satisfied this goal in the population. And in 2010, we should expect that the number of people who succeeded in 2008 will be highly correlated with the number of people who succeeded in 2010, because the number of people in 2010 is a subset of the people in 2008. You had to qualify in 2008, and then we said, what are you doing in 2010? So in this situation, we will usually use the earlier time point as the x variable because we know it from everybody. So temporally, it makes a lot of sense to be thinking about the x variable is the one where we know historically. So that's the 2008 version. So in this situation, on the next set of slides, we've got a couple of things that we're going to fill out. So x in this case is the 2008 total qualified participants from each sampled center. And y is the 2010 total still qualified participants from these centers. B hat will be the total from the x divided by the total, the total from the y divided by the total from the x. These are sample estimates that you got in each of the respective, in your simple random sample, which is the same thing as x bar on the y variable from the SRS divided by, this should be y bar from the SRS divided by x bar from the simple random sample that you have on the previous page. So again, you can take the sample mean on the y variable divided by the sample mean on the x variable. There's the same sample size as 10 in each case, that the denominators effectively cancel out, and you're left with the sample total for the y variable divided by the sample total on the x variable. That's going to be the b hat that you compute once you go through this, keeping in mind that these sample totals are essentially derived by summing up the entire sample, multiplying by the population size, but I'm going to do that on both of these here, so that capital N of 122 also cancels out. So in the Excel spreadsheet, you're going to see me just come up with the total for the y variable for across those 10 elements, and the total for the x variable across those 10 elements. The file itself is in example 45.xlsx. It's under the course notes folder. It's also under the datasets folder in our Canvas page. Here's the setup here. Again, this is the x variable. This is the y variable. You can find this in the Excel spreadsheet. The first tab only has this setup, and it asks you to fill out these things. So if you're not sure what these are, you can go back to the notes originally. And then you can, from these things, compute the overall estimate and the standard error. Now in this case, I don't want a y bar U estimate. I don't want a total estimate. What I want is the proportion. The proportion itself is actually B hat. That's what I want to estimate, the rate at which people are still qualified. So we're actually estimating a B hat in this case, a rate, not a population mean or a population total. So the answer that you're going to clearly see here, which you're going to learn to compute on your own, is about 67% are still qualified in 2010. These are the answers. Please just make sure that you are looking at the Excel spreadsheet and walking through the details as you are. This concludes our third segment. In the next segment, we're going to talk about domain estimation, and then we're eventually going to get in on the regression estimation discussion. Thank you all for joining me. Hope you all are well, and thanks a lot.